Hello everyone. So today let's solve the problem maximum flow. The name itself indicates this one. This is completely based on the flow actually, graph flow, right? So let's see. This was asked in the AIM Tech round 4 actually for the division rated for the division 1. So you can just go through the question. I'll just summarize the question so that it will be easier for us to solve the problem, right? So let's see what the question states here. So we are given a directed graph with n vertices. We have given a directed graph with n vertices, m edges, right? So m edges and binary indicators gi and binary indicators gi, right? So gi for for each edge, right? So just remember this one for each edge, right? So let me repeat this one. We are given a directed graph with n vertices, m edges, and binary indicators gi for each edge. Gi in the sense gi equals, suppose gi equals 1. So gi equals 1 means flow passed through that particular edge, right? Flow passed through that particular edge, right? So this is fine. So what is gi equals 0? Gi equals 0 means no flow. No flow. Flow didn't pass. No flow actually. In simple terms, you can just say here no flow, right? What is our main task here? Our main task is to reconstruct one valid maximum flow network. We have to reconstruct one this one. We have to reconstruct one valid maximum flow, one valid maximum flow network. Nothing but ci comma fi for each edge. Suppose we can consider here ci comma fi for each edge, right? For each edge. This is fine with the minimum possible number of saturated edges, with a minimum possible number of saturated edges. So this one fi equals ci, fi equals ci. So we must output k. We must output k in the sense minimum saturated edges count. What we need to output? Saturated, minimum saturated. I'll just write it entirely here. Minimum saturated edges count actually. What we need to output here? Minimum saturated edges count, right? And fi comma ci for all the edges, and fi comma ci for all the edges, for all edges, right? So just keep this in mind, right? So let me read the question loud. Just listen to this carefully. So we are given a directed graph with n vertices, m edges, and binary indicators gi for each edge, and binary indicators gi for each edge. Gi equivalent to 1. This one I'm considering. Gi equivalent to 1 means flow passed through that particular edge. Gi equivalent to the 0 means no flow. Our task is to reconstruct one valid maximum flow network, right? CIFI for each edge. This one. Yep. Now with the minimum possible number of this one saturated edges, nothing but fi equivalent to the ci, this one. Yeah. Now we must output k. Output k in the sense we have to output minimum saturated edges count and fi and ci for all the edges. So this is about the question basically. Let me delete this one entirely. Now see, we have here NMSNT. So this is nothing but the number of nodes, and you can clearly see here we have one this one first two, 1 2 whatever we have given. This is nothing but the edge. The last one is nothing but the weight. 2 3 is edge, 1 is weight, 3 5 is edge. So I can just draw the graph over here if you want. So let me draw the graph here. So this one, for this particular example, I'll just draw the graph and show you. So this one 1 1 to 2. So next we have 2 to 3 basically. This is also fine. 3 to 5. So let me go with 3 to 5 here. This is fine. 3 to 5. 1 to 4. Yeah. So let me write here 1 to 4. This is also fine. Next 4 to 3. 4 to 3. Let me connect over here. And finally 4 to 5. Let me write it over here. 4 to 5. Yeah. So this is the example that they have considered, right? So this is the example that they have considered here. For from 1 to this one, 1 to 2, we have the this one weight 1. From 2 to 3, we have the weight 1 actually. From 3 to 5, we have the weight 1. From 1 to 4 also, this one we have the weight 1. From 1 to 2 first, this one actually, sorry. From 1 to 4 also, we have the weight 1, I have already mentioned. 4 to 3, we have the weight 0 actually. And 4 to 5, this one we have the weight 1 actually. So this is the graph actually. This is the graph. This is fine. Yeah, this is the graph. You can just note it down actually. This is the graph, right? So here, this is nothing but the n, this is nothing but the m, and this is nothing but the S, and this is nothing but the T, right? So this is nothing but the T. So we have here N, M, S, and T respectively. Yeah, N, M, S, and T respectively, right? So let me delete this one. Yeah, the output that we need to get here is this one. What is the output? We have to output the K, right? Minimum saturated edges count and Fi and Ci for all the edges. Minimum saturated this one edges count is 2, and this one Fi and Ci for all the edges here is this one. Yeah, right? So basically they have given the diagram as well here. The illustration for the second sample case, the saturated edges are marked dark here. See, 4 and 1 that they have marked, right? While edges Gi equals 0 are marked with dotted line. Yeah, they have done here this one, this part 4 to 3 you can clearly see here, this one. Yep. And the integer on the edge is the index of this edge in the input list. Yeah, they have clearly mentioned in the question, man. This is yeah, I hope the question part is completely clear along with the input output part. Now, we have discussed the question as well as the input output part. Next, we have the understanding of the question and the input output. Next, let's do one thing. Let's move on with the approach. Let's move on with the approach, right? So, yep. First, this one. Let's consider the same first example that they have given in the question. This one. They have given in the question for the approach. So, n we have 5, m we have 6. So this is nothing but n. So this is nothing but m, and we have discussed this one already. This is nothing but the s, and this is nothing but the t, right? S we have 1 and t equals 5 we have. Yeah, edges. So this one edges 1, 2, 2, 3. I have already drawn the graph and shown you. So this one I don't have to do it again, I believe. Yeah, out of 5. So this one first two are the edges. This one and two are the edges, and the last one is weight. Yeah. So we have been given three numbers in a line. First two are edges 1 to 2, and the third one is nothing but the weight. This is fine, man. Yeah, the same goes for all the edges and the weight. This is fine. I have shown you the graph as well. Now let's move on with the first step. So before moving on with the first step, let me tell you, we will be making use of the Dinix algorithm, right? So we will be making use of the, yeah, Dinix method or the Dinix algo here, right? So if you know the Dinix, this one, what do we call Dinix approach? I can call it, right? So if you know the Dinix this one algorithm only, you will be able to implement. So I will be implement using the Dinix, this one, what do we call Dinix approach basically in simple terms. Yeah, you have to know the algo at any cost. Again, I'm telling, if you don't know the algorithm, you can just go to the this one graph based algorithms playlist and you can check there. You will get the Dinix algorithm. You can just watch the video and you can understand it. You can come here, right? While implementation, um, implementing, you will not understanding if you don't know the algorithm, right? So we have to know. And Dinix approach or the Dinix algo uses DFS as well as the BFS, right? So we will be making use of the first BFS. First, we will be going with the this one BFS actually. Then we will be making use of the DFS, BFS and DFS both within the Dinix approach. If you know the Dinix algorithm, right? So we'll be making use of the BFS as well as the Dinix algorithm. This one DFS as well, right? BFS and DFS. So here we will be implementing the Dinix algorithm twice to solve this particular problem. Just remember this one. We will be implementing this one twice to solve this particular problem. Right? Let's move on with the first step, man. Let's move on with the first step. So first we will be building the graph. I have already shown you the graph from GI basically. For GI equals 1, as we have discussed earlier, for GI equals 0 and 1 basically. When GI is 1 means this edge carried positive flow, so it must be included in the flow paths, right? So for Gi equals 0, this edge didn't carry, so capacity is still infinity, but Fi equals 0. The dotted line Gi equals 0. This one brighter, that one they have showed, that is nothing but the Gi equals 1. Now what we will do, second step here, we will run the Dinix algorithm. So if you know the Dinix algorithm, we will be going with this one Dinix algorithm, right? So let me mention here, we will run the Dinix algo basically. So Dinix algorithm includes, as I have said, it will we will be going with a BFS as well as the DFS. If you know the algorithm, we will be making use of both BFS and DFS within the Dinix algo to find the minimum cut, right? Source or when I say the minimum cut, it is source or sink reachability. You have to know this at any cost. Again, I'm telling, if you don't know the Dinix algorithm, please go to the graph playlist. So you can just watch the video. You can just try to understand the algo and then come, or else this problem is completely based on the Linux algo. You will not understand anything if you don't know the algorithm. Yeah. So now, uh, we will run the Dinix algorithm that includes BFS as well as the DFS to find the minimum cut. So we will mark the edges crossing from reachable to unreachable vertices as saturated. We will mark the edges. We will mark the edges crossing from reachable to unreachable vertices as saturated. Reachable. This one. What do we call? Reachable. Uh, to unreachable vertices as saturated. This is fine. Yeah, this is fine. Yep. Now, step three. Let's move on with the third step here. Let's move on with the third step. We will build an auxiliary network to ensure GI equals 1. We will build auxiliary, this one network, just to ensure GI equals 1. It just can have flow. This one, GI equals 1, have the flow 1, right? So, but not exceed the capacity, Again, we will build an auxiliary network to ensure GI equals 1. Edges can have the flow equals 1 but not exceed the capacity. So this is the third one. Let's move on with the final one or the fourth one here. So let's assign Fi and Ci. After computing the flow, let's assign Fi and Ci along with the this one minimum number. This one we have to compute the Fi and Ci accordingly with the question. That is also the criteria, right? So I have said that we have to output k, nothing but minimum saturated edges count. Here in this case, we have got 2 in the output. So along with it, we have to output FICI for all the edges, right? So that's what. Here after computing the flow, we have to assign FI and CI, right? So if suppose here within the fourth, so let me continue here. So if Fi is greater than 0, if Fi is greater than 0, then we can just mention here GI equals 1. So if Fi is equivalent to Ci, so this is only for the edges crossing the cut, meaning minimum saturated set. So I'm speaking of minimum saturated set. Minimum saturated set. Yeah, this is fine. Minimum saturated set. This is fine, I believe. Yeah. Yep. Now, what we need to do, we have to output the count k. Count k in the sense edges where Fi is equivalent to Ci and each edge Fi comma Ci and each edge Fi comma Ci accordingly with the question, right? So this is the approach that we will be going with to solve this particular problem. So accordingly with the approach that they have given, so this one, the minimum, this one, what do we call? The minimum saturated edges count is 2, and the edges are this one 3 8 3 4, along with the what do we call, so let me delete this one, this is not visible at all. 2 3 3 3 8 3 4 double 4 0 5 and 4 9, right? So this is the output. So let's do one thing. Now we have the complete idea. We this one, what do we call? We are familiar with the approach. As we are completely familiar with the approach, let's do one thing. Let's quickly discuss the complexities part. So what will be the time complexity and the space complexity? The time complexity for the code that we'll be writing in the future would be this one. What do we call? Biko of E plus V. Biko of E into V, actually E into square root of V, because E into square root of V, because Dinix algorithm is used twice. As I have said, Dinix algorithm will be used twice here, right? So Dinix algorithm will be used twice on the graph of less than or equal to 1000, less than or equal to 1000. So accordingly with the constraints we are going, actually is the less than or equal to 1000 edges, actually, and less than or equal to 100 vertices, less than or equal to 100 vertices. So overall time complexity would lead to big O of E into square root of V. So what will be the space complexity then? Space complexity would lead to big O of V plus E. So why it is big O of V plus E? This we'll be making use of the adjacency list level graph as well as the this one residual capacities, right? So overall space complexity would lead to big O of V plus E. So the time complexity and the space complexity for the code that we'll be writing in the future would be big of E into square root of V and big of V plus E respectively, right? So now, as we are completely familiar with the approach and the complexities, we are good to write the code. Let's start writing the code, right? So first what we'll be doing, we will be making use of this one. What do we call? How do I put it? So we'll be making use of the fast input and the output. So let's this one, import here input output package. So this is fine. Also, we'll be making use of the different utilities. So I'll just go with java.util.star. So this is fine. Yeah. Now let's do one thing. Let's go with the class main actually. Let's go with the class main. You can just go with any class name. I'll just go with the main. Just go that's relevant to the question, right? Just go with the name that's relevant to this particular question. Right, so now let's go with the global constraints and the arrays. Global constants and arrays. Sorry, not the constraints. Global this one constants and the arrays. Right. Let's go with the initialization part. So I'll just go with here. Sorry. Let me go with static here. Final. So this one will be int. I'll just go with a maxim that is equivalent to, let me go with a value. This is nothing but the maximum number of vertices. I'll just go with here, um, followed by three zeros and finally 100. So let me copy the same thing and make the necessary changes. So let me copy this one sometimes. I'll just go with here. Uh, Actually, let me go with, yeah, three times is enough. So this one, let me change the variable name from max n to max e. This one static final int, this remains same. So this one static final int remains same. This one, let me make use of infinity here, inf, right? So this one, let me go with the value actually 10 followed by one, this one followed by basically five zeros, I believe. Yeah. So this is the maximum number of edges, right? So this one I'll just go with five zeros actually. Yep, this is fine. So final int, this one final int in this one infinity. I'll just go with the int actually. This is fine. Int. So let me go with int 10 to the power of 9, nothing but 1e9 here. This is fine. The next one would be, let's go with the graph size, source sourcing, and the edge counter. So this one will be static. So int n m as well as s as well as c. This is also fine. Cn equals 1. This is fine. Next, let's do one thing. We are left with uh, still we are left with many this one. What do we call uh, initialization part? So let's go with a graph representation using the adjacency list man first. Yep. So let me write here static mm, int. Let me go with hd. So this one will be new int of, let me go with maxn. So this is fine, maxn. So let me do the same thing for, so this is fine. So we'll be making use of this one for, we need two, we need next as well, we need flow as well, right? So these three things we need, right? So let's do one thing. Let's do one thing. Yeah, I'll just come here. Int. So let me copy from here actually. I need four, I think. So this one, copy here. This one again, copy this one and give semicolon here. So this one, let me change this one from HD2. So we need this one, right? Two also we need. Actually, this is fine. So next, let's convert this one to, let me give the variable name. Next is also required. Also, we need the variable name flow, right? So we need the variable name flow. So this one is max n for the HD. This is fine. For the two, we need max e actually. So max e, we have number of edges. So this one. For the next also, we are going with the edges itself. We are dealing with the edges. So let me pass max e. And what about this one? Flow. Flow, for the flow also, we are going with the number of edges itself, right? So this one also will be e. Right. So this is fine. Next, let's go with here static. Let me give int here. This is fine. Di equals new int of max n. This is also fine. And current here, so this one will be a new int of, again the same thing, max n. This is also fine. Now let me go with the static here. Int, this is fine. TP, so this one equals new int of 10010. This is fine. uh, U equals, so new int of, so again the same thing, 10010. This is also fine. Let me go with the V value equals the same thing. Let me do one thing. Let me copy paste this one several times so that I don't have to. So this is of the same size actually. So we will be going with the TPU. This is fine. Vertex V, and I'll just be going with IS variable name I double I V IS and double I, right? So three times. I'll just go with this one. Again, this one. Let me paste one more time. So instead of the U, I'll just make this one from V. So this is fine. So this one I'll just go with IS, and this one I'll just go with what do we call? Let me go with double I. This is fine. Double I. Yeah. So yep. One second. This is fine. Let me give the semicolon here. So next thing, what we will be doing here, next thing. So let's, what do we call? So this adds a directed edge, nothing but U equals V with a capacity W, and a reverse edge, nothing but V to U with a capacity 0. In simple terms, let's go with a add helper method. I'll just go with static void. Let me give AD here. So I need the parameters, this one in V edge, this one node U, node V, as well as the weight actually, right? I'll just go with the int W. So this is fine, man. Yeah, now let me go with 2 plus Cn here. So equals V. This is also fine. Next off, I'll just go with the Cn. This is also fine. Let me assign this one to HD of U. Yep, this is fine. Also, let me go with the flow of Cn. This is also fine. Flow of Cn equals, so let me go with the W. So this is also fine. HD of U. This is also fine. Let me assign this one to the Cn. Yep. Uh, Let me copy the same thing over here. Let me copy the same thing over here and let me paste it. So this one too, let's see, and this is fine. Instead of V, let me go with this one. What do we call node U or the vertex U. Yeah. Next of CN, so this one HD of instead of U, I'll just go with a vertex V, right? So this is fine. Of CN, this one equals instead of W, I'll just go with a 0 here. This is fine. HD of instead of U, I'll just make this one V and let me assign this one to CN itself. This remains same. Let me come out of this one entirely. Now we'll be going with a, let's apply the Dinix algorithm. Yeah. So we will be going with a, what do we call? First, we will be going with a BFS. Then we'll be going with a DFS, right? First, BFS we know. Accordingly, with the algorithm, BFS will be making use of the BFS to construct the level graph. So we know this. This is the part of Dinix algorithm, right? So I'll just write here. So again, I'm telling if you don't know the Dinix algorithm, implementation will be difficult. Yeah, you can just go through the graph-based algorithms. There, we have discussed about the Dinix algorithm, push relabel algorithm. There are some algorithms that is related to the this one flow, actually network flows, right? So you can just read this one, you can just watch the video and you can just come, you'll understand this one clearly, right? So this is fine. I'll just go with boolean BFS. This is fine. So within this helper method BFS, let me go with arrays dot fill of this one will be di comma 1 comma n plus 3. So this is fine. And finally 0. This is fine. Let me go with a for loop. So this one will be int I equals 1, I less than or equal to n. N, I'll just go with I less than or equal to n plus 2. So let me increment the I here, right? So let me increment the I plus plus. So this one will be current of I. Let me assign this one to the HD of HD of I. So we are just resetting pointers, man, in simple terms. Now let's go with the level of the source, nothing but di of capital S we have made use of, right? So this is fine. Uh, so this is fine. So didn't I make use of the S here? This is there, right? So why it was not showing in uh, this is fine. Anyways, let's continue, man. So let me assign this one to the 1. Yep, this is fine. Next, let's go with a q. BFS uses q, quite obviously, right? So we are dealing with the integer, which is of the type integer, basically. Yep, this is also fine. So I'll just name this one q, variable q, new. I'll just go with array dq here. This one fine, array dq. So let me complete the syntax here. This is fine. Now let's do one thing. I'll just go with q dot add of, let me pass the s here. This is fine, man. Now let's do one thing. Let's go with a standardized BFS loop. If you know the BFS algo, you have to know the BFS and DFS as well, man. Yeah. So we cannot be discussing entire BFS and DFS algo here. Right. Let's go with a standard BFS loop here. So this one will be Q dot. I'll just go with a is empty here. This is fine. So within the while loop, let me initialize U equals Q dot poll. So this is fine. Yep. I believe this is fine. First thing, we are in this one, right? Removing the first element. So this is fine, q dot poll. Then let's move on with the for loop here for int I equals hd of u. So this is fine. I not equal to 0 we have to go with, right? I hope so. I not equal to 0. And finally, let me assign I equals next of I equals next of I. So this is fine. So within the for loop, let's do one thing. If the edge has capacity left, then we have to assign the next level. If edge has capacity left, then we have to assign the assign next level actually. I can just write it in this way in the form of code. If uh, flow of I, if it is greater than 0, and so di this one, let me write it here to 2 of I actually, 2 of I. This is fine, 2 of I. If it is equivalent to the value 0, then if edge has capacity left, then we have to assign next level, right? So this one will be di2 to I. This is fine, equals di of u, di of u less 1. So this is fine, man. Finally, let's add this one to the cube, 2 of I to the cube. Yep, this is simple. Yep. Now let me come out of this one entirely. So here what we'll be doing, we will return if sync is reachable or if sync reachable basically. Yeah, so this one, let me return here di of t, di of t here. So this is fine. It's greater than 0 we have to set, right? So we have to just return if sync reachable, right? So let me come out of this one entirely. Now let's go with the DFS. We are done with the BFS part. We will be making use of the DFS just to send the blocking flow. So this is also part of the Dinix algorithm. You have to know the Dinix algorithm at any cost. So I'll just go with static here. This one int DFS. So I'll just go with the parameter s as well as the int. So this one in. So within the DFS helper method, so what if we have reached sync? Meaning if s equals t, then let me return in here. So this is fine. The next part would be let me assign a variable out to 0. This is also fine. Next, let's move on with the for loop here. This one int I equals current of this one s actually, current of s, again I not equal to 0. The same this one, what do we call uh, that we have used here, similar one actually somewhere we have used, right? So this one actually I equals next of I. Let me copy the same thing here. So let me copy the same thing here. What's next of I actually? This is fine. Next of I. Yep. Now within this for loop actually what we'll be doing, so we are just going with we are just following the level graph edges here, right? Nothing but the BFS one that we have used, this one, this graph, sorry, this loop actually. Yeah. Now within this for loop we have to push the possible flow. We have to push the possible flow. So this one will be int p equals, let's recurse. I'll just go with DFS of 2 of I. This is fine. And let me go with the math.min of in comma flow of I. Flow of I. So this is fine, man. Flow of I. Yeah. So we are just pushing the possible flow here. So let me go with if here. If p greater than 0, if p greater than 0, then we have to reduce the forward flow, meaning here flow of I, flow of I equals flow of I minus p. This is fine. The next part would be we have to increase the reverse flow. So this one will be flow of I, again XOR 1 equals flow of I XOR 1 plus we have to go with p. right? So yeah, I hope this is fine. Now after increasing the reverse flow, we have to update the remaining flow as well. So I have considered the variable in here, in equals in minus v. Yeah, this is fine, man. Also we have to go with out as well, right? Out equals out plus v. So this is fine. We are left with one simple if condition. What if uh, in equals 0? Then what we need to do if the integer is 0? So we have to break, we have to exit, right? So I'll just make use of break here. So let me come out of this one entirely. So we'll go with a dead end pruning, right? So if out equals 0, same thing, similar to the in actually, if out equals 0, then I'll just go with a di of s. Let me assign this one to the 0, and also let me return here out. Let me return out here. So this is fine, man. Let me come out of this one entirely, right? So this is fine. So somewhere done something wrong? No? Mm, 1 second. Did I miss something here, man? So two for loops I have written. This is fine. So this one I have written within the DFS itself. So this is fine. For loop we have mentioned here. Uh, this one actually equals 0. This is fine. We're just following the same thing actually. What do we call? Oh, this I have messed up something here. I don't know what I have messed up. I have to check this one. Equals current of s. This is fine. I not equal to 0 and I equals next of I. This is fine. This one we are following the basically level graph. This is fine. So next what we have to do here. So within this for loop, so I have to assign the current of s here. So this one to I actually. Yep. So this is fine. Then we have to go with a simple if condition, right? So if, so this one, if flow of I, if flow of I here, if it is greater than 0, so now we are following the level graph edges here strictly. Now, so this has to be di of this one, 2 of I. This is fine as well if it is equivalent to di of s, di of s here, plus 1, di of s plus 1. So then let me increase, so sorry, let me open the flower bracket here. So this is fine. So one more flower bracket I'll open here. This is fine. Yep. So that one I completely left. That one, yeah. Now I have to give int p equals. So this is fine. This is fine. Yep. So let me come out of this one entirely. Return out. So now let's make use of the main method. Yeah, mainly we have written the DFS and BFS and DFS, right? So here let me include throws exception as well, or else we'll be getting the error. So this one has to be throws exception. So within the main method, first we'll be going with a custom this one fast input out for the fast input output. So I'll be going with a custom input output. So I can just make use of the buffer reader and this one print writer as well. So I'm just going with a template. This is completely related to the this one. What do we call? Input output basically. It's your choice, right? So I'll just go with the variable fs here, new fast input output. So this is fine, I believe. Yep. Now this is fine. Mm, let me do one thing. Yeah. So I'll not write this one entirely. So I'll just come here. Let me copy paste the this one. What do we call? Uh, customized fast input output, right? So just give me a second here. So I'll just come here. Let me paste it over here, man. So this is fine, I believe. So this is the this is one of the templates I make use of. Basically, I have made use of this one, right? Whenever the constraints are tight, actually, I'll just go with the this one. Usually when the problem is rated 3000 and plus or 2600 or 2500 plus, usually I make use of the customized fast input output, right? So you can just go with this itself, or you can just go with the this one of your choice. Something that's good template. You can just go with a good template that's related to the input output, right? It's of your choice basically. Now let's go with the number of vertices, number of edges, a source as well as the sink. So here in the question they have mentioned the same. So this one, the first one, this one is number of nodes or the number of vertices. So next one is number of edges, 6. So here they have mentioned 1, 2, 2, 3, 3, 5, 1, 4, 4, 3, and 4, 5. Next one is nothing but the source, and the last one T is nothing but the sink, right? So let's do one thing. I'll just go with n equals fs dot next int. So this is 5. This is fine, I believe. So let me copy the same thing, man, here. Let me copy the same thing here. So I'll just paste it over here, paste it over here, paste it over here. NM SNT, right? So we have in the first line. And let me change this one to M. Then let me change this one to S. And finally, let me change this one to T. So this is fine. Number of vertices, number of edges, source, as well as the sink. So this is fine. Let me come out of this one entirely. So let me go with the first step here. First step, what we are doing, we are just building the flow network based on GI, right? So I'll just go with the for loop here. This one int I equals 1, I less than or equal to m, I plus plus, yeah, I plus plus. So this is fine. First, let's go with a start edge. This one, edge start, edge end, as well as the GI indicator. So these three things we have to go with. Let's go with that one very quickly. U of I equivalent to fs dot next int. Let's make use of the next int, right? So let me copy the same thing for the v and this one TP of I as well, right? V of I and TP of I as well. So we change this one to V from U. Also, let me change this one to the TP of I. So this is fine. Yep. Next, let's do one thing. Yep. Now let's write the simple if condition, man, here. So if TP of I, if it is equivalent to 0, if it is equivalent to 0, I have already written this one AD helper method, right? So I can just write it over here. U of I, comma V of I. Also, let me pass the infinity here. Let me pass the infinity. No flow, large capacity. We are considering here no flow along with a large capacity. So this is fine, I believe. Next, else, right? So else, if TP of I is not equal to 0, then what we will do? So then if the flow existed, then we have to add the edge, right? So with a small capacity, and also we have to add reverse edge for the possible backflow. So these two things we have to do. Let me do that very quickly. So this one will be AD of U of I. So this is fine, comma V of I. This is also fine. Then let me go with 1, right? So AD. So this one will be V of I. So this is fine. So this one will be U of I. So this is also fine. Finally, let me go with the infinity. Yeah, so this is fine. Yep. Now, let's do one thing. We have to go with the, we have to compute the maximum flow, right? So again, did I miss something here? 1 second, just give me a second here. Mm, I don't know, man. Let's continue. Let's continue with the algo actually. Implementing the algorithm, we have to compute the maximum flow, right? So let's go with the first phase here. So I'll just give here int su equals 0. This is fine. Sorry. Let me come out of this one entirely. Now I have somewhere I have done something wrong. Else this is fine. Oh look, this is also fine. Mm, this public void. This is fine. This yeah. 1 second. So this one will be removed. If condition I'm using here, this is fine. For loop I'm using here, I'm closing here. If condition else I'm using here itself actually. Else I'm giving here, this is fine. Yep, let's do one thing. Let's continue, man. Let's continue with this one, computing the maximum flow actually. So I'll just give here int su equals 0 initially, and we have to run the Linux algorithm here. So let me go with a while loop here. while so let me make use of the BFS here, right? So BFS, let me call the BFS function helper method that we have written, sorry. So this one will be SU equals SU plus DFS of S comma infinity, S comma this one infinity. Yep, this is fine, I believe. Next, let me go, let me print the flow value, right? So minimum number of saturated edges actually, right? So we have to print the flow value, nothing but here uh, we have we have to this one going with the or printing the minimum number of saturated edges here. So this is fine. While BFS of you, this is fine. So let me go with fs dot out here, fs dot out dot println. So this is also fine. Let me pass SW. Let me pass not the SW. We have made use of SU, I believe. Yeah, here SU equals 0. Just above. This is fine. Now let's move on with the next step. Nothing but we have to determine which edges are on minimum cut accordingly with the Linux algorithm. So now let me write the iteration part. Let's move on with the iteration part. So this one will be I equals 1, I less than or equal to M. So this one will be I plus plus. So within the for loop, made use of the variable is, s of I equals, so this one will be di of u actually, u of I. So this is fine. U of I, if it is not equal to 0, and so this one di of, so this one will be v of I, v of I. So this one, if it is equivalent to 0, then we have to display 1. We are just making use of the ternary we are just making use of the ternary operator. Else we have to print 0. This is fine. Next part would be let's reset the graph man. I'll just go with arrays dot fill this one quickly. I'll just go with a hd comma 0. After resetting the graph, let me assign cn to this one. Actually, 1. This is fine. Also, let's connect the sync equal source, right? Since sync that is equivalent to the source, right? So this one I have already written. AD helper method. You can just check above. This will be t comma s comma infinity. INF we have made use of, right? So I'll just choose this one. This is fine. So the next one is we have to go with the new artificial source as well as the new artificial sync. So this one will be s equals n plus 1 as well as, so this one t equals n plus 2. T equals n plus 2. New artificial source as well as the new artificial sync. Yeah. Next, let's move on with the next step. Nothing but we have to build the new auxiliary network. We have to build the new auxiliary network. So let's go with a simple for loop here. So this one will be int I equals 1, I less than or equal to m. Let me increment the I. So this is fine. So if here within the if condition, if tp of I, so if it is equivalent to 1, then let me go with AD of so this one U actually, AD of U of I. So this is fine. AD of U of I, comma V of I, comma V of I. So let me pass the infinity as well. Let me pass the infinity. We are just keeping the large capacity here, right? So I'll just go with II of I. So this one II of I. So this one within the array. Yeah, this is correct. So let me assign this one to the CN, the variable name that we have considered. Finally, let's make use of the helper method AD that we have made use of S, comma. So this one will be capital V of I, as well as we have to pass the 1. So what we're doing here, so we are considering from the artificial source from and to, right? So this is from, again we have to go with the 2 actually now. So I'll just copy the same thing here. Let me copy the same thing here. Let me paste it over here. So source we have considered 2 is nothing but u, right? So we have to go with the u of I here. uh, U of I. So this one too we are considering. So capital T here, the variable name that we have considered. And so this one has to be 1 itself. This one will remain 1. So let me come out of this one entirely. Now, the next step is we have to run the flow again to adjust the FI value. So this is the reason I said we will be running the this one Dinix algorithm, or we will be making use of the Dinix algorithm twice, or we will be running the Dinix algorithm twice, right? So we'll be previously I had said that we'll be making use of the Dinix algorithm twice, right? So again I'll just go with while here. So this one will be BFS. So this is fine. Also let's go with a DFS of what we have to pass S along with the source along with the infinity. Source along with the infinity. So this is fine, man. Next step, what we will do, the next step, so we have to construct the output. So let's go with a for loop here. So this one will be for int I equals 1, I less than or equal to m. Let me go with I plus plus here, right? So within the for loop, what we'll be doing, let's go with a simple if condition here. If tp of I, if tp of I, if it is equivalent to the value 0, then let me go with fs dot out here dot println. So this one will be println, println of, let me go with 0 as well as the 1. Let me go with 0 as well as the 1. No flow edge we are considering, right? Fi we are pointing to 0 as well as Ci we are pointing to 1. So now let's go with else what we'll be doing, let's compute or let's calculate the actual flow. So this one will be int, so this one will be int val equals flow, flow of, so this one I double I of, let me go with the I double I of I. So this one is fine. 1 plus 1, actually we are just calculating the actual flow. After calculating the actual flow, what we have to do here, so we have to consider the saturated edge as well as we have to consider the not saturated edge. So that how can I write here, simple if condition here. If is of I, if the value is equivalent to 1, then I'll just go with fs dot out here, fs dot out dot this one. Let me go with the println. So let me go with val. Let me append here. We need to have space. You can just look into input output there. This one within the question, and also let me append val here. So this is fine. We are considering the saturated edge, and also we have to consider the not non-saturated or not saturated. So else let me go with here, else fs dot out dot, let me go with a println. Again we have to go with the same thing. Well, let's, so this one let me go with a space here, and I have to append infinity instead of the this one, what do we call, um, infinity instead of the val, because this is not saturated, right? So first we'll be having the value plus space as well as the, we are considering infinity here. Simple. Now let me come out of this one entirely. The final thing is we have to flush all the output. Let me go with fs dot out dot flush. Yeah, fs dot out dot flush. Yep. So this is it for the code, man. We are done with the coding part. So this is it for the coding part. So let me do one thing. So let me come here. Let me do one thing. Before checking the code with the different this one examples of the inputs, let me copy paste the signature starter template. So let me come here. Let me paste this one over here. I'll just come to the question. Let me copy this one. The output that we need to get here is this one. Yeah, let's check the same. Oh, we have so many errors, man. 10 errors. Okay. Else without if. Where? Line number 89. This one I was also having this some kind of this thing actually. We have methods of the if. So this is within the main method actually. This is within the main method actually. Let's check the same one. So here, hmm, line number 96. What's your while of BFS? What happened here? Illegal start of type. 1 second, just give me a second here. So let's see what we have done here. So this one else actually, what is wrong here? If this one I have made use of here, this one, this is fine. Yeah. Mm, let's do one thing. Let's try to fix this one with actually here itself. Let me give this is fine. Let me remove one this one. This error has to be gone now. Yeah. Uh, illegal start of expression. So what's wrong here? This is fine. So actually, there was some this thing actually. What do you call? Typos actually I have corrected that one. including actually braces misplacement and some variable names. This one, right? So I'll just pause the. You can just pause the video and you can just look into it. So I'll just giving this one the code actually. I just want to show you the code. The same thing. There was some typos actually. The corrected ones. You can just look into it. Yeah, this is fine. I believe. Let me scroll this one. Yeah, DFS function. So this is fine within the main method actually. Yeah. So you can just have a look into it. This is fine. Yep. Finally, this is related to the this one, what we call input output. Yeah, this is fine. Now let me run this one. I hope this works, man. Yeah, now we are getting 10. This is fine. 1 second. So here, this is also one of the valid outputs, right? So this is also valid output 23338 3444, and we can have the multiple outputs they have strictly mentioned in the question. See here, if there are several possible answers, print any of them, and this is one of the possible answers as well, right? So this is one of the possible answers. We are getting the correct output in my opinion. So whatever we have went with the pure this one, Dinix approach actually, Dinix algorithm, right? So I hope this has to work actually. Let's see. I have implemented the same with whatever the knowledge on the algorithm I have. Let's see. So let me choose here E and let me paste this one and let me hit the submit button. I hope this works for all the test cases. Let's see. Let's wait for some time. I hope this works, man. Yeah. There was some this one typos actually I have corrected. You can just pause the video and you can have a look into it. If you are this one practicing along with the code, the same thing, then you can just pause the video and you can just have a look into it. I'm just scrolling slowly. Yeah, this is fine, I believe. I'll just scroll from over here. You can just look at the code from here. So I have mainly fixed that one within the main actually. BFS and DFS is fine within the main actually. Yeah, this is fine, I believe. Yeah. Yep. Yeah. Now you can clearly see here the verdict that we got here is accepted. So whatever the code that we have written works absolutely correct for all the test cases, right? I hope the solution part is completely clear, man, along with the approach and the complexities. For now, this is it. Thanks for watching, guys.